All right, so let us start on time, more or less. Good morning, everyone. My name is Eyke Hüllermeier. Let me welcome you to our tutorial on the topic of aleatoric and epistemic uncertainty in statistics and machine learning. Also, of course, on behalf of my two co-presenters, this is Victor Banks, who is also from my own group in Munich. We are both from LMU Munich, and Wilhelm Wagemann from University of Ghent. Victor asked me, first of all, to let you know that the slides are also available online on the tutorial website. So you can have a look in parallel and also download them there. So yeah, first of all, it's nice that you made it. Friday, last day of the conference. Yesterday was conference dinner. So it's good to see so many people here. Also, I hope you don't mind the sound in the back. We don't know exactly what that is, but there is a technician taking care of this. I hope so. No, he's not coming. Okay. So then it will also be fine like this. I will start with a short introduction, then we'll hand over to Victor, then it's Wilhelm's turn, and in the end I will come back with the third part of the tutorial. So let us start with a brief introduction. What is our tutorial actually about? Oh. Okay, so yeah, basically it's already in the title. It's about uncertainty in machine learning. And the topic of uncertainty, actually it's a relatively old topic in machine learning and more generally in AI. Some of you may know there are even whole conferences dedicated to the topic. The conference on uncertainty in AI is like 40 years old or so. So uncertainty has been an important topic from the very beginning of AI, and for a very good reason. Recently, it started to attract renewed interest, I would say, in machine learning. And one obvious reason is that nowadays, machine learning methods are really applied almost everywhere in practice. And many of these practical problems are very safety critical. So you don't want to make fatal mistakes. Here you see one typical example. On this picture, you see a standard supervised learning scenario. You observe some training data. In this case, it's X-ray images tagged with positive, negative, for example, depending on whether or not a certain disease is present. From this, you learn a predictor, could be a neural network, could be any other machine learning approach. And you make use of this predictive model in order to make predictions for new instances that have not seen so far. And the state of the art, I would say, in machine learning is to not just make a deterministic prediction, yes or no, but at least to provide degrees of probability. So to make a probabilistic prediction. Yeah? So for example, 0.8 positive, 0.2 negative, in order to reflect some certainty or uncertainty of the learner. There are many other examples of safety critical applications. Here you see just one connected to autonomous driving. This is taken from one of our ongoing projects. And yeah, everything, of course, which has to do with autonomous driving and so on is also highly safety critical. And I could continue this list of applications with these properties. Now, as I said, probabilistic predictions are more or less state of the art. The question, of course, is, the crucial question is, can we really trust these predicted probabilities? Yeah? How confident can we be about these predicted probabilities? How uncertainty aware actually is our machine learner? And you easily find examples where this completely fails. So here you see one state-of-the-art neural network here was trained in the fashion domain in order to classify objects on an image. And here, for example, you see, you can't see, it's maybe too small, but For this left image here, the learner predicts umbrella, which is obviously wrong, as you can see. On the right, it predicts a skirt, which is also wrong. And actually making mistakes is maybe not so bad. Also, we as humans, we do make mistakes when we classify pictures, not in these cases, but maybe in some other cases. But the problem here is that the learner does not only make a mistake, it is highly confident in its prediction. So here it's 97%, here it's 96%. So extremely confident. And this is actually not what we want, yeah? It is fine when the learner makes mistakes and is uncertain in some cases, but in these cases, it should also reflect its uncertainty in a proper way and say, hey, maybe I'm not really sure. Maybe I prefer to abstain or do something else, but in any case, not to be overly confident. So what we observe in practice is often a lack of this uncertainty awareness that we actually would like to see. So ideally, as I said, when making a prediction and predictive uncertainty, this will be our main focus today, uncertainty in the prediction that the learner makes. Of course, one could consider various other sorts of uncertainty. Ideally, the learner knows what it knows, and maybe even more importantly, it knows what it does not know, yeah, what it doesn't know. And this requires, first of all, an adequate representation of the predictions the learner makes, for example, in terms of distributions or sets. This will be the main two types of representations that we are going to present today, and a quantification of the uncertainty, for example, in terms of, most of you will have heard about such measures like Shannon entropy or so. So here you see, in terms of terminology, we make a distinction between representation and quantification. Yeah, representation is a mathematical object representing uncertainties such as a distribution or a set, and a quantification is a single number, a single scalar number, quantifying the amount of uncertainty, how uncertain actually is the learner in a current situation. As well, of course, if you want to provide Q-valued predictions, where the Q is, as I said, a distribution or a set or whatever, then you also need a machine learning algorithm providing such Q-valued predictions in a faithful way. If the learner, for example, predicts probabilities, we expect that these probabilities are somehow well calibrated. Yeah? Willem is going to speak about this in more detail. And in this regard, it turned out that a distinction between different sources and types of uncertainty is actually quite useful for various purposes. And our focus today will be on a distinction that has recently also attracted quite some attention, namely aleatoric, what we call aleatoric and epistemic uncertainty. Aleatoric means inherent randomness, and this is a type of uncertainty that is irreducible. I will speak about this more in the third part of the tutorial. Epistemic uncertainty is uncertainty that is caused by a lack of knowledge, because the learner doesn't know better, but in principle, with additional information, it could get rid of it. Here is my standard example to explain the difference between the two types of uncertainty. If I ask you in a coin flipping experiment, what will be the next outcome of the coin toss? You are uncertain, of course, and if you know that the coin is fair, then at least you can say it's 1/2 probability. If I ask you what is the meaning of the word Kichwa in the Swahili language, I guess most of you will be as perplexed as in the first case, as uncertain. I can tell you it's either head or tail, so it's one of the two, but which one? Yeah, you are as uncertain maybe as in the coin flipping example. However, the important difference now is that you could easily get rid of this uncertainty, but by asking Google or nowadays ChatGPT, of course, yeah. I use this example even in the in the pre-ChatGPT area. But now probably ChatGPT will provide the answer, or maybe not, I'm not sure. Maybe someone can try. But in any case, you could easily get rid of it or just look in a dictionary or so. Okay, and this distinction between aleatoric and epistemic uncertainty, this is an important point we would like to get across. This is also important in a machine learning scenario. Just as a teaser, so to say, here is a very simple example trying to make this point clear. So here you see a situation, binary classification. The learner has seen a few examples, positive, negative, and now has to make a prediction here. And yes, you will probably agree that is somehow a case of uncertainty. Yeah? So the learner is not certain whether this is a positive or negative case. And the main reason for this uncertainty, we could say, is of epistemic nature, because only seen few data so far, doesn't know very much, especially in that region here. Here it's basically the same scenario, but now with more data observed. Yeah. And the same point to classify, the learner again is uncertain whether it's positive or negative, but now the difference is that this is, so to say, confirmed uncertainty. The learner is sure that it has a good reason to be uncertain, which is not the case here. Yeah, maybe with more data, the situation could have been clearly in favor of positive or clearly in favor of negative. One final remark from my side. It's not only the amount of data, of course, that plays a role in the learner's certainty or uncertainty. It's also the prior knowledge the learner starts with, what is typically reflected by the learning bias or the representation bias. So, for example, if the learner knows or has good reason to believe that the data can be separated in a by a simple linear model, then even with this little data, it will be relatively certain that this here is a positive point, simply because all the models that are plausible given the data will predict positive. If the learner weakens its assumptions and also allows for nonlinear discriminant functions, then again the situation is more uncertain, because some of the plausible models will say positive, other plausible models will say negative. And this is also very natural, namely the stronger, let's say, the prior knowledge is that the learning process is starting with, the more the data is actually telling us, and the more confident the conclusions in the end will be. All right, so this ends my short introduction to the topic. Here is an outline of the rest of the tutorial. As I already said, it essentially consists of 3 parts. The first will be given by Victor, who is recalling some basic statistical concepts that are always useful to have. Yeah? And then in the second part, Willem will speak about, we made this distinction you see here between what we call first order and second order uncertainty representation, and you will later understand what we mean by first order, second order. Roughly speaking, that's not exactly true, but roughly speaking, first order corresponds to aleatoric, second order corresponds to epistemic. Yeah. All right. So, and with this, unless, maybe I should mention, I guess this is okay, right? Whenever there are any questions, please feel free to raise your hand. It's not such a big crowd. We should keep it interactive as much as possible. And with this, I hope I didn't forget anything important. I hand over to Victor.